Now as we got the values of AV, AVS, AVL and AVSL, now we'll calculate the another theoretical values with the some formulas. So first we find the AV, theoretical AV. So AV is equal to GM into RD. So we need to find first what is the value of GM. So as we know, the current and the voltage is nothing but here GM value. So we can directly obtain the value. The current is 1 milliampere and the gain is 50 millivolts. So it will come across 0.02 Siemens or more. So if you multiply 0.02 into RD, which is nothing but 0.02 into 2.2 into 10 raised to power 3. So this will become across 44. So our theoretical AV is equal to 44, which is again get matched with our practical value. So this is what the AV calculation. Now we can find the AVS. So AVS can be found as AVS is equal to AV into RI upon RI plus RSG. Okay, so we know the AV value. Again, we know the RI value and RSG value. Simply put the value in the equation, then we can find the RI is equal to, I can directly write your equation over here, or value is equal to here 17.73. So again in the previous page we have calculated this value, so that will be equal to 18.6. so now we are getting the value 17.73, so it will be approximately equal. Then AVL we have to find. So again the formula is AV into, this is RL upon RL plus R. So again this can be found as 13.75. in the previously we have find it the value, which is 14. So again that values get matched with your new theoretical value. So this is how we can correlate the practical calculation with the theoretical calculation. So all the practical and theoretical calculation is matched. So now we'll see how will be the effect of the source bypass capacitance and the internal capacitance on the frequency response. So for a frequency response, I just draw some diagram to understand the concept of frequency response. Means what? In the frequency response we get two plots. One is a magnitude plot and another is a phase plot. So we know that the input and the output of an amplifier having phase shift of 180 degree. So we can obtain the phase shift of 180 degree in phase plot. So if it is in 0, so 180, and at lower side 180 we can obtain the phase shift. Again for the magnitude, so this is how a frequency response can be observed by any amplifier. So this is nothing but a mid frequency gain. So this is a mid frequency gain. Okay, so this is an magnitude we can say, and this is a frequency. So in the mid frequency the gain is constant. So now we have observed the gain is 44. So somehow we can observe the gain at this point is around 44-46 practically. Okay, now this is an output voltage. So for finding on the lower cutoff frequency and higher cutoff frequency, so if you consider the power losses or the voltage losses of 50% of the total power, so if I consider 50% for total power loss and total power is 100%, so it will be 0.5. So if I consider it with the dB, decibel, so for how much dB it will be decayed. So if I take that 10 log of 0.5, then it will come across minus 3 dB. So this will be a reduction in the power at the lower cutoff frequency and the higher cutoff frequency. Now if I convert this minus 3 dB into the linear scale, so it will come across 0.707, which is nothing but the 1 by root 2. Okay, so now if I multiply this 0.707 with the amplitude or with the mid frequency gain, so if I multiply 45 into 0.707, so it will come across 31 point something, so 31.5 I can say. So if we reduce the, if we find out the gain 31.5 at the lower end and 31.5 the higher end, so we can obtain directly the higher cutoff frequency and the lower cutoff frequency. So this will be FL and this will be FH. So this is about the finding out the higher cutoff frequency and lower cutoff frequency with consideration of power losses. We can also take the relationship between the voltage. So this is V by VO, or we can take by power P by PO. So we have considered 50%, or we can consider 70%. For 70% again we can obtain the 3 dB power losses. So for 3 dB we can obtain the value, it is 0.707. You can also calculate it on your calcs. So if the minus 3 dB is divided by 20, so how we can obtain the value of it? If minus 3 divided by 20, so we can get an answer. And if I take the power of 10 of it, then again it will come across 0.707. So this is how we can obtain the frequency response. So now we'll just go to the simulation part. Now here we are having the all our circuit. I just changed the value of this source bypass capacitor with its initial value. It is 100 microfarad. And now go to the simulate part, analysis, AC analysis, output. So here I have already taken the equation, that is V5 divided by V4. So what is V5? V5 is nothing but the output and V4 nothing but the input. So the output divided by input, so that transfer function response we need to observe. So I can click on the simulate, see. So this is what our frequency response. I will take the cursors over here. So this is cursor 2 and this is cursor 1, see, and this is the reading. So if I move the cursor 2 into the mid frequency gain, the gain is constant. So if you look at the Y2 position, so it is 45 and we obtain our gain is 44. So this is a mid frequency gain. Now if you want to find the lower cutoff frequency and higher cutoff frequency, we obtain the equation, that is we obtain the value, that is 31.5. so I can move the cursor x1 and find the x1 value, and when the x1 value will be at about 31 or 31.5, I'll stop over there. So now yes, so y1 value is what? 31.5. so this will be our FL, and again at this side I'll just take it at the middle. So at this side again for 31, yes, so this will be a lower frequency. So this is y1 value, this is x1 value. So x1 is about 33.20, so this is 33 Hertz, and at the higher end we can obtain the value of x2, it is 4.2 megahertz. So if I take the subtraction from FL to FH, so it is come across 4.6 megahertz. So this will be your bandwidth. So again at the lower plot, again take a cursor over here at the lower point. Again we can see over here 0, this is a phase 202 200 02 minus 200. If I again take a cursor over here, so at this point, so this is cursor 2, so I can check the value of y2, this is y, so you can check the y2 value is minus 179.9, means 180 degree. And if I take this value at the uppermost side over here, again it will come to 179.9, means what? 180 degree. So we can directly observe the transition from the input to the output at 180 degree. So this is how we can observe the frequency response and can find out the mid frequency gain. So now we can change the value of source bypass capacitor. I can close this. So let's change the value of source bypass capacitance. So I'll take its very small value. So it will increase the impedance of that branch, and now the current will flow from the RS. So we can have the voltage drop across RS, so it will affect on your output. So how it will be affect on output or frequency response? So again, go to the simulation, AC analysis, output, and simulate. See, now again I'll take the cursor. So look at the figure. So in previous figure we are having wide range of frequency band. So in here the band is get reduced. Okay, so if I take the again 31%, so the now frequency it will be in between 28k to, this is what, X2 4.072 megahertz. So see, it will be affect on your lower cutoff frequency. So the lower cutoff frequency will get affected due to the source bypass capacitance or source bypass capacitor value. So the lower side frequency will get affected on that, so we'll get the less bandwidth, so it will affect on the bandwidth. Now again we will check out how the external capacitance, that is shunt capacitance, to be get affected. So what is shunt capacitance? So if you look at the figure, these are the capacitance, because a MOSFET is made up of different material. So we are having N type and P type material, so they are isolated with certain material, so certain isolations are there, so there may be a chance to develop a capacitance. So these are the internal capacitance. If the internal capacitance is more in some cases, or it will be developed in the amplifier, then how it will affect on your frequency response, that we are going to see. So for that purpose I have connected an external small capacitance value of CW. So if I increase the value of CW, or if you take the some example, you can take some less value or normal value, say in nanofarad, so how it will affect the output response, so that we are going to check. So again I change the value of it to its original value again, so this is 100, so it will affect on your lower cutoff frequency. I connect this, so it is 2 nanofarad. So just sorry, so go to the simulation, and this is AC analysis, output, all are set. Look at over here. Now this is our first figure, this is our second figure when we change the source bypass capacitance, and this will be our third figure where we are connecting the external capacitance, that is internal capacitance. So that is shunt capacitor, this is shunt capacitor effect. So I'll again take the cursors, again mid frequency is same, again I will check it for x1 value, which will be x1, and y1 value, which will be 31. Yes, and y2 and x2 value, so this will be 31. Now look at this, the higher cutoff frequency is reduced drastically, so the frequency bandwidth is drastically get reduced at higher cutoff frequency. So initially we got the 4.6 megahertz, now we only got the value of x2 is 37 kilohertz, so it will be between 28 or 33 hertz to 37 kilohertz. So now this is how the capacitor will get affected, or the effect of the shunt capacitance on the performance of the amplifier. So the bandwidth get reduced, so the source bypass capacitance and shunt capacitance will also have the effect on the frequency response. So the source bypass capacitance will affect on the lower cutoff frequency, and this shunt capacitance will affect on the higher cutoff frequency. So this is all about experiment number 2. On the same line, we can again discuss the experiment number 3, which is nothing but the current series feedback amplifier, in which we can also find out all these parameters with negative feedback. So this is all about experiment number 3. Sorry, experiment number 2.